Yes. Thank you. Thank you for having me here, or us here. I'm Torsten. You can interrupt me during the talk if it's okay with the audio. Okay, I have to thank my funding agency, and I have to, something went wrong. Okay, there should be a number. Yeah, I have to thank many people who actually did the work I will present. In particular, Philipp Arras, Jakob Knollmüller, Reimer Leike, and Philipp Frank is here with us. They changed the game and made possible some of the newest results I will present. And actually, I will not present alone. Philipp will present part of my talk, or basically the work he was more involved in than myself, and he will give a tutorial on the numerical methods with which he achieves the things I will present tomorrow at a time still to be communicated. Okay, we have these fantastic instruments that scan the sky, like your Mercat, and they deliver data. And we want to get back to the sky from the data. However, the data is finite, but the sky has an infinite number of degrees of freedom. At each location of the sky, the brightness could be different. At each frequency or at each time, it could be different. So we have a strongly ill-posed problem to infer many more degrees of freedom from a few which we have measured. And these are even contaminated with noise. It might not cover every location. So mathematically, that is not possible to invert this directly. However, if you fold in additional information on what could happen on the sky, of what we know about the sky because of physics, or because we can assume that the sky is different parts, it's not completely different, then we might be able to break this degeneracy. So let me introduce a very simplistic model which will appear over and over in this talk as one way to do this. We could say the sky is composed out of diffuse emission and point sources. It's of course more complex, but let's start with that. Then we have to say, what are these things? Well, point sources are, on first sight, statistically independent, right? They can be very bright, very dim and next to each other, and don't need to be correlated, but they might be drawn from common statistics, which might be valid for all locations on the sky. Diffusion emission, on the other hand, is correlated. So if you know that one location, you have an idea what is at a nearby location. And if you go further away, this idea might get more and more vague. However, you can exploit this, that if you have a measurement at one location and you know about this correlation, then it helps you to get a good guess about neighboring locations. Okay. So we want to measure a signal. So all these quantities I will call in the following the signal, the quantities we want to know. We want to infer or several signals from data. So let's look at this with the theoretician view. So there's a huge high-dimensional space of potential signals, because at each artificial pixel on the sky, the value it could be different, and so that's one dimension. If you pixelize the sky with 1 billion pixels, then you have 1 billion dimensions. In that space, you want to find a location. Then we have our data space, which is also very high-dimensional, but finite dimension. What we would need is some structure in the space to orient ourselves, and this comes in, And what we want to do is to do basically logic. We want to do reasoning in this space in order to translate data into estimates of the signal. But we have to deal with uncertainty, substantial uncertainty. And we can show, and this has been shown, that logic extended to the realms of uncertainty leads to probabilities. And probabilities have here to be understood as quantifiers for statements. How sure are we that something is true? Not how often is something not true. So you see, I will use a Bayesian definition of probabilities in my talk, not so much the frequentist, which restricts probabilities only to how often are in a certain configuration, but as a way to describe our knowledge on the quantity, which might not have any statistical spread at all. We just don't know its value. Okay, so we want to know probability theory in that space. And I said we have to somehow specify what we know about the signal we want to know about the sky, and that could come in form of a model. And if we do this, we might be able to specify the a priori probability for the signal. For each of these signal configurations, we can say how likely the data configuration could be. And that is an instrument model which specifies this likelihood. If we manage to write down these probabilities and encode our knowledge about the sky and about our instrument, these multiplied together define then a joint probability of all the things that can happen in our signal space and our data space. Now, if we get the actual data down here, we know that we must be somewhere on this hyperplane. We just have to cut this high-dimensional probability distribution and say now, okay, let's choose locations in here, look at them, and normalize them in a way that the probability again is normalized to 1. And this can be easily done by dividing this by appropriate normalization constant. And what you end up is space theorem that we all know, love or hate. It is. Can move the signal away. Is there a way to get this real signal? Someone knows the trick.
If we get into the possible the screen sharing thing, or
more, more. Press one more. On more, there's a way to get this away. Hi, did you come? No. Oh, should be this side. Yeah, I can be straight. That's okay. Take it from here. Good. A Bayes theorem is the foundation of information theory. So here's Bayes theorem again, and I rewrite this now in a way you have learned in your statistical mechanics course as E2 minus some energy divided by a temperature which is set to 1, divided by a normalization constant, right? As a Boltzmann distribution. That's just a very simple mathematical trick, because if I just defined this energy here as the negative logarithm of the joint probability to make this work. And I call this quantity information. It comes under many names, it also often called surpriser, but I like to convince you that actually this is not so far away from the natural language word information we use. Because we can do operations with that, and in particular, if we go to this coordinate system, it's just a coordinate transformation, we can exploit the methods developed for statistical mechanics and thermodynamics in order to do inference of signals. The normalization constant is just a rebranding of this so-called Bayesian evidence over here into a partition function, which is just the normalization, so integrate for the joint probability is an unknown signal for the given data. Yeah.
So normally Bayes theorem, you also have the prior, right?
Oh, this is prior times likelihood.
So it's all included.
It's all included. I was skipping over that.
Okay.
So here you see it's written in if.
Right.
Here you see probability for the signal.
Yeah.
So where I'm on this axis, then after I've chosen an axis, where do I get into data space conditional to the signal?
Right.
And these two multiplied together define this one.
Oh, okay. So that's where it's
Yeah, I was a bit
okay. Comma instead of
comma. Yeah. The
Okay.
comma is
I
an
missed
end.
that. Sorry.
Yeah. I was jumping on this. The comma means an end. So data has a certain value and signal has a specific value. The slash means conditional. So the data is unknown, and it's assumed that the signal is known in this expression. So the joint probability can be deconstructed in first the probability a priori for what is a signal, then given that, what is the data? This multiplied together gives this, which is this numerator. Yeah, and here I wrote it in that form in order to make this transition. But we will get to this in a second, namely here. Here's exactly what you asked for. This joint probability is prior times likelihood. And if I translate this simple product rule of probability theory in this logarithmic coordinate system, see what happens. The logarithm turns the product into a plus. And now we see, if you call this quantity information, that information is additive. I can add in the information. I have the information a priori plus the information of my data. That's fantastic. All good things in life are additive, right? Money, energy, love, all additive. Information as well. And it's so great that you can even.
Is the information the exponent or?
Yes, it's updated for exponent.
It's not really additive. It's ones that being multiplicative.
Now, the probabilities are multiplicative, and if I take the logarithm, it becomes additive. It's very simple. It's just going to a different coordinate system, and I'm doing this because once you look at this, then you can do statistical mechanics, and you have learned it in an elementary school in physics. That's the only reason. You could also work and do everything up here, right? But most of us are physicists, and therefore, and physicists have developed a lot of methods in order to deal with Z formulation. So that's why this changed. Okay. Yeah.
For the sake of grounding, is the information like equivalent to the physicist like entropy?
If you take the expectation value of this, then you get over the same distribution, then you get the entropy. So, and that's why I call the entropy the expected information, where this is then the information. Okay, it's additive. So if you have two instruments for using data 1 and data 2, and they were independent, then you can just add them up. If they were dependent, the measurement process, well, then have you put the dependency in here. So you can use this for data fusion, putting several instruments together, adding more knowledge piece by piece, removing knowledge if you don't want to put it into your analysis, but want to see whether your data wants a certain thing, so you can play with it. You are actually allowed to play with this. This is, you formulate questions. What does the data tell me in the light of certain assumptions, or in the light of more data? You can do such experiments with that. Okay, we want to do information theory, but for fields. So for continuous quantities, what is a field? A continuous quantity as a function of space or time or energy. And here's such a field. And this has many, many degrees of freedom. That's a dust field of the galaxy. And we have to constrain them because in principle, there's an infinite number of degrees of freedom. We have only a finite number of constraints. But I already told you, if you know something about the correlations of the field, then if you know the correlation structure of the field, so how different points in space are correlated with each other, and you have a guess for all pairs of points, then this is also an infinite number of constraints. They might be vague, but their sheer number regularizes a problem. On the computer, we can't work with this continuous limit. We have to discretize the space into pixels. But in order to keep the flavor of this continuous space, we have to request that this pixelization can be refined and refined until nothing changes anymore in the result of our analysis. So what we are going to do is to set up field inference problems in a way that the discretization in the end, it does not matter. You can increase it and you get the same results. So we want to do information theory for fields, for short information field theory. That's what it is. Bayesian reasoning for fields. And it means that one has to deal with the space of all field configuration, and that's a functional space, and has to do probability theory over that. And that's what for which mathematical physicists have developed statistical and quantum field theory to deal with such things. And one can use techniques like Feynman diagrams in order to derive estimators for field properties, like here an estimator for the non-Gaussianity because we might have background. But more importantly, one can apply this to real data. So here to radio, CMB, or gamma ray data, as I will show in my talk, and Philip as well. In order to do that, information field theory is a theory, you write down equations, you have to solve these equations. And for that, you have to use computers. And my group is providing this nifty package, the numerical information field theory package, which allows you to do such things on your own laptop. What is Nifty? It is a differential programming, probabilistic programming language or library in Python. What does this mean? Well, it allows you to program such models with a few lines, and then you can run them. They start with random numbers and form these random numbers into something which looks like diffuse emission or point sources and the sky signal, and then in the end the data. So you can run them as a generative model to simulate mock skies and mock data. And I will show you that. What it also allows you is to invert this, to put in data and ask what are all these degrees of freedom above. They are not uniquely determined because often, in most applications, you have more freedom up here than the data constraints. So there will be uncertainty, and there's the probabilistic element coming in. Well, Nifty allows you to explore to some degree the remaining uncertainty after having fixed the data in your model parameters. Okay, Nifty allows you to easily program field inference, for example, here, one-dimensional case. Changing one line in that code can turn it into two-dimensional inference on the sphere or even on product spaces like sphere times and energy axis, as you will see later. First, let me tell about how to implement correlations. And let's do this a very simple example with the simplest example we can think, an image with only 2 pixels. So S1 and S2 should be brightness values of these 2 pixels, which we put into a vector. Let's assume we know something, that there's a positive correlation between S1 and S2, so that the prior probability for S1 and S2 is like here, when S1 is positive, S2 is positive as well a priori, and vice versa. So that's what we assume to know in advance. Let's do a measurement of S1. So our data is S1 plus some noise. No statement about S2 from the data. We can map out the likelihood, what it says for as a function of S, and it wants to constrain S1. So S1 should be here, no statement by the data about S2.
So I have a quick question. So is this assuming correlations of all orders?
Oh, in this case, I have not specified what kind of correlation, and you probably saw that I am doing some Gaussian assumption.
Okay.
But it has to be something else.
Okay.
Correlation. So it doesn't have to be linear correlation. It can be
Okay.
Yeah, but in this simple example, deductive example I use, you will see that I will use Gaussian correlations.
Okay, thanks. Yeah.
Okay. So we get some information from the data about S1, but no about S2, but we have our prior knowledge that says that whenever S1 is positive, S2 should be also positive. And the base formalism tells us, well, to multiply these things together and to renormalize, and then we get the posterior, which tells us, yeah, S1 is positive, and as a consequence of the prior, S2 is positive as well. That was a prior. Now to your question, in this particular case, let's assume it's a Gaussian statistic, just to keep things simple. So the prior statistics of S is an exponential of a quadratic form in the signal, and in the kernel of the exponential function, there's this inverted correlation function, correlation matrix. And this is just the a priori expected correlation between the different pixels, S1 with itself, S1 with S2, and S2 with itself. Okay, that's basically all the math one needs in order to do with 2 pixel images, if Gaussianity can be assumed. But you might want to do more pixels. And the nice thing is this formula still holds. You just have to make this correlation matrix n-dimensional, n times n. And even further, you can let the number of dimensions go to infinity if you want to deal with a continuum of locations. So now the correlation matrix became a correlation function tensor, depending on continuous locations x and y, and it encodes how different pixel locations are correlated. In several situations, we can make further simplifying assumptions. namely that the correlations of these 2 points over here are the same than any other points with the same distance. So if our knowledge, a priori knowledge, does not single out any specific location because physics is homogeneous, then this might be a good assumption. And if this is true, that the 2-point correlation function does only depend on the distance of these 2 points or the direction of these 2 points, but not on their location, then this correlation function is just a function of that distance. And one can show with a Wiener-Khinchin theorem that it becomes diagonal if one goes to Fourier coordinates. So let's switch to Fourier coordinates. We have done the Fourier transformation of the field, and here now the sk and sk prime. Now this correlation function is diagonal, no cross correlation between these Fourier modes. And but they are differently excited, as you can see. This is not so much excited than Z, and this is encoded in the diagonal of this correlation tensor now. And the quantity is called the power spectrum, simply the Fourier power spectrum. And that allows us, so specifying this power spectrum specifies the correlation structure, and therefore this Gaussian statistics. So that is a language in which we can model correlation structures. It's very flexible because that's a function. We have a lot of degrees of freedom still here. And that could be our most simplistic model for some diffuse emission. And in most applications, you see we actually will use that. Okay, so now I can build up this generative model I spoke about. We specify the correlation structure with the help of a power spectrum, here shown on double logarithmic scale. Very often power spectra are power laws. So on double logarithmic scales, just a line. Like Kolmogorov turbulence is a characteristic power law. But things can be more complicated, so we allow for deviation from that. So we put also a Gaussian random process on top of that. That allows for deviation from power laws. So as a flexible language, in order to formulate what could happen on the sky, about which at the moment we know do not want to put much information, just that things could be correlated. Okay, so we set up a process to produce such power spectra. Then these power spectra define how the correlation of a diffuse emission field might look like. And here is now a random sample drawn of such a diffuse field, which had this as a process power spectrum. We could continue our model building by introducing luminosity functions, point sources, draw a sample, add them up, and to have a sky with point sources diffuse emission as a generative model. That should be a model of our.
Yes. So are you saying that the power spectrum is the same all across the sky?
At the moment, yes.
Okay.
Yeah.
So
And then there are cases where this is stupid assumptions, and then one should do something else. But for the moment, that's what we do. Yeah. Okay, so that is a generative prior model, and one can ask, okay, how flexible is this prior model? Could the real sky be in it? So let's draw a few samples from it. Here's a sky realization. Another one. Oh, another one. A wild one. Maybe more reasonable one. You get a feeling. You might have spotted that the granularity of the diffuse emission changed from sample to sample. So we do not specify the correlation structure. We say it's an unknown, and so these were prior samples.
So the images come from the correlation structure?
So the diffuse part of the image comes from the correlation structure. So points in here come from that branch. And so we just said there are two processes on the sky that at the moment should explain everything. Okay. And if you say, oh, but there are more, okay, then we add more branches.
Are you doing something about like a UP cutoff for them? Because you don't want an inverted spectrum that explodes, because then you won't have a Gaussian like.
Okay, so yeah, good point. So you saw that we had the slope.
Yeah.
And we say that's a random the slope is a random process as well. We put a prior which prefers falling spectra.
Okay.
Just because for most of the signals we have seen, there's something like a unique cutoff.
Yeah.
However, we do not enforce it.
Okay.
So inverted spectra are possible and sometimes happen. And you could change the prior as it does. And they're not a problem.
Is it just because you're doing the sky, so you have compact space, so you're fine? Because if you have an infinite space, right, and you rise to infinity,
at
And-
UV,
And in UV, then it's,
you get very small scale structures, very strong small scale structures. It's not a problem because if you data don't like that, it will cut away that part of
Yeah.
the prior space which has these inverted spectra. So the problems you have in quantum field theory with UV or infrared cutoffs are usually not present here because as soon as the data comes in, many of these things are cut away.
Yeah.
So we also have an infrared, often an infrared singularity a priori, but the data usually tells us, well,
so the data,
forget about the infinities.
the data regularizes. itself.
The data grounds you. Yeah. Good. Yeah. So that gave you an idea about the prior. Of course, we want to work with data, so one has to add a process to describe how the data was generated. So a digital twin of the instrument and statistics for how the data was generated. That was the generative mode. Now we want to invert this. Probabilistic. So we want to plug in data and ask what could these quantities have been given that there are statistics defined which say certain things are more probable, something are less. So we want to do a probabilistic inversion, and that defines a very high dimensional posterior distribution, which might be complicated shape in a and which are depicted here. So what to do with that? Most people do maximum or posteriori, so search for the maximum of this posteriori and say this point corresponds then to my image. That goes well if your models are not too deep. You have a relatively flat model. With this, you can already run into trouble because first there's an ambiguity here, and then very often we want to appear the correlation structure as well. And what is important is that not only it's important how likely is a point, because you will never meet a point exactly. You will never find the real truth. You will always have something which might be close to the real truth. So the volume, the area's volume in this phase spaces matters. And these volume effects can differ largely because we are in millions of dimensions. Maximum a posteriori is one spot which often overfits and might be a very untypical spot, and there might be less likely spots, but with a much larger volume involved. And so we need techniques to explore the volume. Such exist like Hamiltonian Monte Carlo, but that's very expensive. So what my group does is we fit a Gaussian. Fit a Gaussian in a million dimension. So the mean of that Gaussian are a million parameters. The covariance structure are a million times a million parameters, 10 to 12. You can't store it on computer. Fortunately, a very bright student, Jakob Knollmüller, found a way to approximately parameterize the correlation structure as a function of the location by using the Fisher metric. And that's why his method is called metric Gaussian variation inference. All of the results I will show you are using that techniques, which shifts a Gaussian in high dimensional space and takes the correlation between all parameters approximately into account. Yeah.
I'm unclear about one conceptual thing.
Yeah.
This inversion problem.
Yeah.
At a very high level, the method needs to decide whether to put the flux in point sources or diffuse emission.
Yeah.
So
both is possible.
what is the control parameter or whatever?
The
How do you
power
tell it?
So the point sources have a wide power spectrum a priori. They're uncorrelated.
Sure.
The diffuse emission is usually prefers smooth things. And so anything that is very rect would easily be described by this point source part of the model. Anything which is smooth is more easily explained by the diffuse emission part, because fewer degrees of freedom of our top level degrees of freedom have to be excited in order to generate a diffuse structure with a diffuse model, whereas with a point source model, you have to, at each location, you have to put something up, whereas a diffuse model might just excite a few Fourier modes. So the play between prior assumptions on these two components. The funny thing is the prior assumption of the diffuse emission is partly inferred from other parts of the image because we infer the correlation structure simultaneously with the data. So I'm not saying that there is a unique answer to that, but very often our algorithms find solutions or prefer solutions where we human would say, oh, that fits to additional physical knowledge I have about the situation. It's not perfect yet. No, but this is only the prior information. The likelihood doesn't care. Okay. Okay, that is metric Gaussian variational inference. But you see directly, it's not a perfect description of this probability distribution. Therefore, another extreme bright student named Philipp has developed geometric variational inference, where he puts on top on the top layer of our models another layer where this this posterior gets mapped to another coordinate system where it becomes our posteriorly roughly Gaussian. So that's like a normalizing flow, which you might know from machine learning, but without training. So Philipp managed to find this coordinate transformation approximately just from the model. If you use Nifty or package, then you can use either MGBI or GUBI, depending on how much accuracy you need or how fast you need the examples. So let me switch to examples. Here is a Fermi satellite, and let's look at the data of the Fermi satellite in the light of this model. Here are the photon counts recorded by Fermi on the sky back projected. Color coded is the energy of the photons. Blue means high energy, red means low energy. And then let's do the inference. And that's how the sky signal looks like. But we have these higher levels of that model, so we can separate into diffuse and point sources and ask, okay, what looks the diffuse emission component like? And it's like this. So here you see diffuse gamma ray emission between a GeV and 300 GeV or 500 GeV, color coded in a way that spectral information is encoded in the color. Bluish means hard spectra, reddish means softer spectra. You can do directly astrophysics by eye.
I'm a little confused here. For that picture you showed, you have information all over the sky.
Yeah.
Right. So there's nothing, you have perfect data everywhere.
You have very good data, yeah.
Very good data.
But
So
noisy, but okay, no.
what
Okay.
is the inference though? Are you looking?
So the inference is happening, well, you see these point sources are spread, so we take out this point source function. Also you see this color speckle, which means these are individual photons which you see at different energies, and we turn this into something continuous as a function of the position on the sky and as a function of energy. So you have.
How would this method compare, for example, to just looking at nearest neighbors and doing some kind of localized spline fitting or localized averaging?
Well, this is doing localized averaging, however, in a way which is optimal for the local situation. So it's self-adapting. Of course, it can only somehow average the data. The data is exciting, but how do you average? What is the kernel you use? And do you use the same kernel at each locations? And this method said, no, here I have many photons. I can use a very small kernel to convolve. Here I have few photons. I use a larger kernel. Here I have a point source, so I actually have very poor information on my diffuse emission. So I just extrapolate what comes from the outside. All this is done automatically with formulation. You don't have to.
It is guaranteed to be optimal. And if so,
In a certain set, well, if you forget about the approximations we used, and if you say the information you encoded in the prior, then yes. Well, that's if the information you encode in the prior, of course, is not so good, you could have used better, then something else would be on the. But we have a figure of optimality and we try to move towards that. We don't reach it perfectly for numerical reasons and so on. But yeah. So what this image is actually is the posterior mean calculated within the approximations we do.
I'm sorry, can I ask one more question?
Yeah.
So So one thing we do in the EHT often is we start with the sky.
Yeah.
So we know what the answer is.
Yeah.
And then we take synthetic data
That's what we
and
do as
we
well.
corrupt it with the known engineering response. And then we attempt to reconstruct it, and we can compare it to what we really knew.
Actually, that's what we're also doing here. So this is happening internally. So when we plug in data, so what we do is we throw in some random numbers, calculate synthetic data, then look at the difference between the synthetic data and the real data, weight it with what we know about the noise, and then ask, okay, how do we have to change the parameters of our model up here in order to make this discrepancy smaller, but not smaller than necessary, right? Don't overfit the data. So this is a fancy way of doing chi-square.
I think you said earlier that the point sources were white noise, but don't these physical point sources have their own correlation function?
Oh, yeah, so, yeah. So
Okay.
I also said the prior is just a statement about what we decided to assume.
Okay.
The assumption doesn't need to be correct. So we assume no correlation. The data wants a correlation. The data gets a correlation. So if there is a correlation, we have shown that there is a correlation in the real world, not due to our prior. Of course, we could say, oh, let's exploit it further. Maybe that helps us to get out more point sources. Yes, you can do. But if you ask the question, is there a correlation between point sources? Don't put it in the first place. Use a stupid model as we do. The data tells you there are correlations. Oh, we discovered something. Then, okay, can I use this to make better images? Yes. Yeah, that was my playing with the assumptions statement.
Yeah, just sort of a practical question about how you get these point sources. Your model isn't producing an arbitrary number of point sources, right? You have a about where they are located.
We have a point source at every location, at every pixel.
I see.
And most of them are also different. So our prior is tuned such that most of them are invisible.
But they're basically co-located with the pixels. And
Yeah. So at every locations we have a diffuse emission field and a point source field.
I see. You somehow choose.
The algorithm chooses, right? The inversion chooses. But okay. Here's a diffuse emission. Okay, I could talk for hours about the astrophysics of that, but you are interested in imaging. Here is starlight absorption by dust. Okay, so here you see the blue stuff is inverse Compton scattering. The red stuff is hadronic interaction of cosmic ray protons and molecular clouds. The clouds contain dust, and the dust can be seen in starlight absorption. We can set up models for that as well. Here's such a model. And actually, since we have distance information from the stars, thanks to Gaia, it is a 3D model. So what you see is in a cube with 800 times 800 and 600 parsecs around the sun, which is in the middle, the dust distribution in our local vicinity reconstructed from 100 million lines of sight of stars, I believe. What's the exact number? That's the local superbubble. Now we get back to the view towards the galactic setup. Okay. So these were 10 to the 8 degrees of freedom, for which we have also the correlation structure of the uncertainty. So 10 to the 8 times 10 to the 8 matrix, which we never store on the computer. Okay. If you project this back on the sky, that is that part of the Milky Way that we reconstructed. So you see the nearby dust clouds where they are on the sky. We only reconstructed some part of the galaxy. If you compare this to dust emission, where dust absorbs starlight, gets warm, and therefore emits in the infrared, you see that there's also the galactic band, but these nearby dust clouds, I think we got them relatively right from absorption data. How much did we reconstruct? Well, here's a Milky Way, and we reconstructed this, so there's still more to be done. That's roughly the volume we got. And here's a top plane view onto it, showing the local super bubbles and other bubbles, and the ISM community got really excited about that, and there are many follow-up papers. This was a real game changer in the field, because a year before, reconstructions looked like that. That was done here in Harvard, like in green, and that was amazing at its time. But it was taking correlations only along individual lines of sight and not across them, which will count, and therefore the image fidelity is a bit less. Okay, you guys are most interested in things which are in the center, like these. And many of you were involved in the Event Horizon Telescope, and I don't have to explain you that you do interferometry, which constrains actually stripy patterns on the sky, like one baseline. You have several baselines, and you can do superpositions of these stripy patterns, maybe get some image information, so-called dirty image, back projected data. We worked with such data as well, and developed the resolve algorithm, which I want to show you. So that's a dirty image of Cygnus A. This is a clean image. That is what resolve does. I hope you see the difference in image quality. There's noise, no negative flux values because we excluded them a priori. If you look at the hotspot area, much more resolution. If you look at higher frequency in clean maps, we see the same structures. So they're real. We get more out of the same data. But
can you over resolve?
Yeah. So we can show we do super resolution automatically. If the data is good enough, we do automatically super resolution.
And what is the super resolution depend on?
On the single noise ratio, so how much and how well you describe your transfer function and all these things.
These have super resolution.
Yeah, I believe so. Yeah, definitely, because for radio astronomer standards, resolution is defined as a Gaussian fit to the dirty beam. And you convolve your image and then you get this. See, we have more resolution than what that does. Yeah, but you're interested in that. And I think Philip should talk about what my group did to M87.
So, Torsten.
Yeah.
Did you have point sources in that Cygnus A image?
Yes. Two.
You allowed
two. And we have to admit we put them at we put them at locations of known point sources. In this case, so we didn't have the point source fields. Yeah.
Okay.
Yeah. Radio astronomy is tricky. The calibration is hell. And we started to do this by ourselves. The problem is that actually, as the ionosphere moves the images around, and if you don't tell the model that this happens, it can't find a consistent solution because it says, if I put a point source here, but the data wants the next moment here or there, so it's inconsistent, and then there's no point source. So radio informatic imaging with point sources is really difficult. So we started on self calibration.
Thank you. Okay, so let me use a few minutes to show you what we did with information field theory on the 2017 observational data that we got from EHT on M87. I guess I don't need to introduce this source to any of you guys. So let me spare the introduction and let me skip to what we tried to bring to the table. Torsten already made a fantastic introduction. So we are inherently interested in treating these things probabilistically. So ultimately, what we try to reconstruct is the posterior distribution of the sky brightness given the observational data, subject to some additional assumptions. And the most important assumptions that we wanted to put in addition to the data is that this sky brightness is strictly positive, so no negative flux is physically plausible. So we want to really exclude this a priori, and we want to exploit correlations in all its dimensions. So not only spatial correlations, but also we want to exploit the fact that there are correlations in time and frequency. So these are the two main assumptions that we wanted to bring to the table and bring into the analysis. And this already has a few very profound practical implications. So first of all, the only way to do this consistently is to use all the data at once. So especially if you want to exploit the fact that things are correlated in time, the only way to do this is in a holistic approach. So we really set up a space-time cube for both of the frequencies, and then compare this to the observational data of all the days that were observed in a probabilistic fashion. And just to throw in some practical numbers, so this results in this case, in a 7.5 million dimensional influence problem. So the posterior distribution becomes a function that makes the match from 7.5 million dimensions to a real number, and basically assigns a probability to every possible configuration that is possible a posteriori. But it also is rewarding because this includes all the knowledge that, given the prior and the data, we have on the source. So especially also including the certainty that we have on the knowledge. So it has an intrinsic way of quantifying uncertainties and telling us how certain we are about structures on the sky. So what do we get? So this is the image that we got for the first day of the observational cycle. And so we can compare this to what we got in 2019 from the HT collaboration. So this is we compare this to the first day using HT imaging, and while these images look slightly different, what we found is mostly they're very consistent. So we do get more or less the same structure that was already found by HT, which was reassuring to us. So we get a slightly bigger ring and a slightly thicker disk. Overall, the image looks slightly more blurred. We mostly attribute this to the fact that we have this intrinsic uncertainty quantification. So if things are not that certain in the mean image, they will look more blurred. And we have a little less side lobe structures. This is basically they're the time correlation hubs that you have a time continuous and time consistent image. So some of these type of structures disappear.
So one question.
Yeah.
In the model, did you say there are no point sources?
Yeah, this is only diffuse emission.
What would happen if you allow point sources?
If you allow point sources in here, so since you only have very, very bad data, let's say, what you will get is a prior dominated result, which means you will get something that looks like this ring, but the decomposition is some realizations will explain this using point sources.
Yeah.
Some will explain this using diffuse emission. It's much easier to explain this with diffuse emission a priori. So you will have more a posterior probability on diffuse emission, but you cannot rule out explaining all of this by point sources. So I will get a little bit into how well constrained the posterior landscape is in a second, and then all right, so but since we did this not only in space but in space and time, what we actually finally got out was a time continuous video. It's pretty hard to see, but there's actually some movement happening. So this is the full the time lapse over the full 7 days of the observational cycle. And that is basically what we get as the mean result for the HT data. But since I said we want to do this in a probabilistic framework and in a probabilistic setting, so we not only get one mean image, we actually get many. We actually get a whole posterior probability distribution over videos, over plausible videos, given the prior data. And here are 16 examples. And as you can see, while all of them look like rings, there is still quite a lot of variability left in these images. And this is to connect to your question. I would throw in point sources here, I would just get even more variability, and some of these rings would look even more freckled, let's say. So how did we get there? First of all, let me say that these are actually all consistent videos. So this is a nice verification to just look at what would each of these videos imprint into your measurements. So if you would take this as your true sky and measure it, you would actually see all of them. These are three examples for three closures, and we actually get all of them more or less track the data equally well. So there's, from the data alone, there's no way of deciding which one of them is better. but let me show you a little bit what we used in the end in practice to maybe differentiate also a little bit. I mean, first of all, the data that we got is, or that you guys got, that we were fortunate enough to use, here's the UV coverage for the 4 days. What we ended up using in the end is only closure information. So we basically wanted to avoid the effect of antenna-based calibration artifacts. So we based our entire analysis on closures only. That was after experiments for us the most stable and safest way to proceed here. I guess I don't really need to introduce closures to you as well, but I mean, the most important thing that was troublesome for us is that you lose a few global pieces of information, like absolute position of the source and the absolute brightness, using closures only. So this is something that we had to deal with in the analysis, and it also produced some artifacts along the way. In addition to the closures, we used one of these correlated field models. So here is an example. So this is basically throwing random numbers in one of these generative trees, generative processes that Torsten just showed, and generate a random realization of our prior to get a feeling for what does this prior allow and what does it do. And what we can nicely see is that not only the image is correlated, so you not only have correlation within the image plane, but also individual images at different time frames and for different frequencies are correlated. So this is really trying to explore correlations in all directions. But since we can't impose this correlation structure exactly, what we only want to impose is the existence of correlation. So rather than saying this is how stuff is correlated, it might also be correlated like this a priori. So this is just another random realization or a bit more moderate one. And treating correlations a priori as unknown in a probabilistic way means that also a posteriori, the correlation won't be fixed completely. So the data can only tell us so much about correlations. And one can nicely see this in the videos that not only are the shapes a bit different, but some rings have a little more small scale structure, some have a little less small scale structure, some actually very more significant in time, others less. So this is basically the posterior uncertainty that's still left in the analysis on the correlation structure, in addition to the uncertainty on structures as well. And now to verify this, I think this is picking up Shep's question initially. We also applied this to mock examples and mock data and mock setups. So basically using static and dynamic ground truth sources, generate data from that and trying to do the fit and the reconstruction to see if we really get out put in. And overall, we found this to be a rather convincing result for us. So the pipeline seems to be fairly general in the sense that you can throw in things like these double sources and also get them out. This comes at the cost of being rather slow in the sense that we don't put in a lot of prior knowledge, and this means that the reconstruction is more expensive because we want to a priori not rule out anything at this point. I think now that we're convinced things are a ring, one can move forward in a bit more aggressive fashion, let's say, but this was we wanted to be as agnostic as possible in terms of prior information at this point. We also looked at validation runs in the sense of how stable is the pipeline. And what we did here is we took all the hyperparameters that we have around the pipeline and sampled them in a predefined regime, then did 100 runs with different configurations. And what we found there is that for more than half of these runs, we get exactly back out what we had in the initial pipeline. So in that sense, it's quite stable. We found a small subdominant runs that looked the same in an image, but actually didn't show any significant dynamics. So these were basically static versions of the reconstruction. However, what we saw is they have significantly larger data residuals in the results. So this was another convincing argument for us that the data actually wants dynamics. So the data residuals for both the mock setup and also the actual data was significantly larger for these examples. And then we also found a few of these funny non-physical results. These are mainly artifacts using only closures in combination with a prior that also doesn't put any information on the source structure. So having source copies, having two sources looks fairly similar in a closure-only setup to the measurement. We also had one very funny thing in videos is source warping, since there's a big gap in the observations. We only have data for the first 2 days and the last 2 days. We actually had results where we had a very nice ring for the first 2 days, and this ring suddenly disappeared and reappeared at a different location for the last 2 days. And while I don't know if people actually considered the physics of teleporting black holes, so far, I think we can rule out stuff like this is not physics. So with this, let me wrap this up. Let me finish and get back to Torsten. So the key things that we wanted to bring to the table is, first of all, doing a holistic approach using space, time, and frequency reconstruction. At the same time, putting in correlations, but only in a very agnostic fashion. Only the existence is there, and if the data wants them, they can exploit them. And do this whole thing in a probabilistic setup, which is actually a necessity once you really want to also infer the correlation structure. If you don't do this probabilistically, it's prone to be very, very difficult and inaccurate. But the reward is an intrinsic uncertainty of quantification. So we can really say what structures are real, at least in an approximate sense, and what not. And with this, let me give you back. Let's change here. And Torsten's going to tell a little bit about artificial intelligence.
Yeah. Artificial intelligence is a big topic, and the question might be, well, very often one gets asked, oh, how does this differ from artificial intelligence? And I want to say, not at all. This is artificial intelligence. Okay, how does the network architecture looks like? I said, oh, I already showed you. Here it is. That's my neural network. I put in random numbers and do local nonlinear and non-local linear operations in, oops, what happened? I stepped on the tail on the cable. Maybe yeah. And non-local linear operations in sequences. That is a neural network. It's a generative neural network. We set things up that we start with Gaussian random numbers, and then they generate signals and data. And when we infer things, that corresponds to how you learn if you train a neural network. But these things do not need to be trained. They are self-adaptive, so they extract certain features, correlation properties of your signal and use it in order to improve the display of others. Okay, so if this is a neural network, can we interface it with custom neural networks from the shelf, which represent knowledge of certain, say, images? And the answer is yes. Jakob Knollmüller shows that one can take a usual network which has encoded, which has learned something, produce a signal, then code a very bad instrument which adds noise and corrupts the data, and get some data, and then uses this data in order to see what all these quantities are. I don't know if you can see what it is, but the network completed that image with this. The network knew about the existence of faces, so it was a face generating network. But in this architecture was run in matrix Gaussian variable inference, so we got also uncertainty information, and these are posterior samples of possible images of that person which are shown. I have to add that two other networks where they are present there, one which made statements which classified this gender and one which classified the age, and the age and gender information was also added in order to constrain that. He leaves this away a few men would appear. So ground truth in this case looked like this. So maybe a little bit of an overfit, but you see one gets a feeling of the well reconstruction and the uncertainty around. Okay, we conclude our talk. Information field theory is a form of artificial intelligence. It's designed for big data. Most important, it's for you. You can use it. It's open source. There's a web page with some nifty package. There are resources, papers on it. My lecture on it are online. And tomorrow, at a time still to be specified, you have a chance to do it on your computer. You come to Philipp Frank's tutorial in this room, right? Yeah. Thank you.
Thank you both. We have time for a couple of questions.
I'll let that.
Who was first and
Yeah, so I was curious about the Feynman diagrams on the. So I know that the Feynman diagrams, if you get loops, you get like unitary representation, without that you just get tree diagrams. Like how does that? How do you? I see. Is it just?
for the tree diagram, the sum of all tree diagrams correspond to maximum a posteriori estimator, and the loops are exploring the uncertainty space around this. So they are uncertainty corrections.
So I guess so.
They appear only in nonlinear problems. So if you have a linear problems like Gaussian signal, Gaussian noise, and linear response, the loops are, well, actually, you don't have these three vertices because then you get them.
So a given diagram corresponds to a given information, I guess, from the beginning of the talk. And so the information is like.
So I would have to go into a few technical details, but these dots at the end, they basically the data noise weighted back projected into your signal space. These lines are the propagator applied to this, which are the uncertainty covariance in a Gaussian approximation to the problem. And these vertices corresponds to nonlinearities, which might come from non-Gaussian statistics or nonlinear response. And I'm happy to explain you how Feynman diagrams appear. But what are Feynman diagrams? They are expansion of a non-Gaussian distribution along the Gaussian distribution using a small parameters. In this specific case, it is about CMB and non-Gaussianity in the CMB. So, and many of the models for, in particular, this local CMB non-Gaussianities say there was a Gaussian random field, which then non-linearly got processed into the CMB. And this non-linearity might summarize some inflationary physics or gravity or what else. And one can describe this in this case as a point-by-point quadratic interaction of the initial field. There's a parameter in front. And then you have this parameter as a parameter. You write down the evidence of your data given that, and the log evidence is a log partition function. And if you remember your QFT questions, the log partition function is the sum of all single connected Feynman diagrams, which you order then in the ones which are linear in order, which are up here, and which are quadratic in that parameter, which are down here, and then you solve for the parameter, and this gives us the formula. That's the short version.
So I guess like with the CMD story, it's more natural that something like this would pop up.
Because we have a small parameter here.
Yeah, so it's not as obvious how you like map this on some other problem.
In the other problems, you don't have a small parameters, and then the Feynman diagrams, they are only in asymptotic expansion, they converge terribly. So as soon as you have a strong nonlinearity in your problem, and all interesting problems, most of you are interested in now of that kind, that doesn't work very well. Then one can do resummation and techniques. One can do effective action techniques. And then I learned at some point, I realized, oh, this effective action from quantum field theory is corresponding to what the imaging community calls variational inference. it's exactly the same. So why not doing variation inference in the first place?
Yeah,
That's how we got to this place. But at the beginning, we were doing Feynman diagrams through summation and digged our works through this mathematical concepts. In the end, it turns out, okay, variation inference is a good approximation.
Normalization.
Again, on the large scales, the data is normalizing, and on small scales, in this case, it's about the CMB. So this estimator is respect to some cosmology which has a falling power law. Yeah, so in this case, this cutoff is imposed a priori. Okay, yes. Okay.
Sure, yeah. I'm curious about the, and you guys mentioned a little bit about this, but how the sort of separation is enforced in the Fermi maps between the diffuse and the point source structures, when naively you might imagine that they could trade off between one another at sufficient resolution and comparably describe the sky emission, but somehow your parameterization in this correlation domain enforces the preference to use the diffuse emission where possible.
Yeah.
Do you understand how that separation really plays out under the hood?
Roughly. Not as well as we like, but roughly. So for the point source at each location, we assume that there is a point source, and we assume an inverse gamma prior for them, which with a mean luminosity which is invisible here. But inverse gamma is not as restricted as the Gaussian statistics, so it allows easier for larger deviations the data has. So okay, so why is this modeled as a point source but not as diffuse? As diffuse would mean that you have to excite many Fourier scales in order to have a localized thing. That needs that, so that has to work against many prior information, right? So there are many springs pulling it back for the diffuse. So it's much easier just to pull one parameter up in order to explain a point source. Then if you have a diffuse structure, of course, you could have excite at each pixel a point source to some level. But then a blob like this is described with a few Fourier components with wavelengths on that scale. Many less than that. Also, they might work against a stricter prior, a Gaussian one. They don't have to excite that much. So it's really this interplay.
And somehow the parameterization in your, I guess, power spectral space is okay. All your explanation very, I think so.
Yeah,
and the
and
number of parameters doesn't seem like it's much different. It's just somehow the distribution of the impact of the image of a particular parameter changes between the point source and the parameterization in the power spectral space.
So in order to get structure like this, in the our diffuse parameters live actually in Fourier space. And I only have to excite a few in order to get a blob like that. I have to excite many in order to make it with point sources. And for the point sources, it's vice versa. So only one in the point source field has to be maybe put away. But in the diffuse, I would have to excite many.
It also helps a lot that the actual point source distribution is fairly sparse compared to the coverage. So if you look at the pixel where the point source is in isolation, you're right, this is completely degenerate, but conditional more or less to the nearby surrounding, it's then the degeneracy is broken a lot by the fact that you have also diffuse measurements around.
That's a really nice separation.
But it's also not great.
Who's next?
Well, I'm just going to grill you later at dinner.
Okay.
So.
Then,
I already asked the question.
so maybe you first.
So yeah, so for the point source model, then you're not assuming like some induced sparsity prior or something that says most of the pixels are on and then most of them are like small amounts are on.
When is implicitly there?
Is it just because the inverse gamma? Did you have
Yeah,
to
the inverse gamma. It has a huge tail which allows pixels to get very bright, but most of them are comfortable to be not visible at all.
You even like thought about doing
So
something?
that is a sparsity prior.
Yeah. You haven't thought about doing something like a stick breaking process or something, or some like spike and slab model where it will really like push it either on or off type thing?
No, it's continuous here.
Oh.
One could think about transferring these point sources to another model where you really have a point source which can move around a little bit.
Yeah, I'm thinking it's like spike and slab will have something like you'll have an inverse gamma, and then you can put a delta function at the origin. So it'll give you some probability weight, and then you tune it so that it's, or you can learn it.
Yeah, so you could do this by applying basically a mapping from the brightness, and the lowest part is then mapped to exactly 0.
Yeah.
So this advantage of that is it's not differential anymore. And I told you Nifty is a probabilistic differential programming language, so we exploit differentiability of our models.
Yeah.
It doesn't break down completely if you break differentiability, but some of the assumptions which are baked into this I don't hold exactly anymore. The sampling helps. There's a sampling which is imposed in MGBA or GBA. You already see that there's coming up. So maybe but these are so dim it doesn't matter. They are orders of magnitude below the diffuse flux. So if you put them really to 0 or be there,
yeah, it can just kind of sometimes help if there's like some dim source, or it just helps turn it off and maybe give it a little more. You're probably a little prior dependent, but no,
if you feel more comfortable with a model like that, it's very easy to modify this. No,
So I guess a question about the MH7 movie. So you mentioned that you log code amplitudes and closing phases, and there's this, you lose a constraint of the flux and the position. So I guess the way how I think about this as a gauge degree of freedom. And what I introduced is that you have a gauge volume that you have to integrate over, which each solution corresponds to, and that would, you're just doing a naive integration that slows down the computation that has made like the algebra necessarily. So did you figure out a way how to get around that issue?
No, we actually do the exact same thing in a sense that we reconstruct a normalized. In the end, we reconstructed a normalized linear. So we take the whole space-time cube, integrate it, and divide by it to divide out this degree of freedom in the forward process. But actually, compared to, because in order to enforce the correlations in Fourier space. So basically, doing Fourier transformation of the entire cube is actually more expensive than integrating over it and dividing by it. So basically, this extra computational step, compared to the most expensive step in our forward process, was negligible in the cost. So yeah, and the position degeneracy we basically ended up fixing by tweaking the initial position. So we start by fitting to some broad centralized shape, and then use this as an initial guess, rather than really starting from a random distributed flux. That helped a lot with double sources and stuff like that.
Yeah, we should probably continue our lunch. So let's thank our speakers again.
Thank you. Thank you.
Thank you. Very nice.
That was fun.